interesting application. So binary search is a very good or very useful strategy for algorithm design because it's log n time complexity, especially as we saw, if you take constant time to decide how to decide which subproblem to go further down. Alright, so here the problem is given a function which is again monotonically increasing or decreasing. So in the case of this problem, I said the array has to be sorted. That's a kind of a monotonic function where the values, let me remove this, where the values are either decreasing or increasing. See, you can apply one thing you should know when you go for interviews, they may try to test you. So when I say sorted, the array need not be just sorted in increasing order. The array could be sorted in the decreasing order also, and you could still apply the same binary search strategy. So don't think it has to be always sorted in the increasing order. You can apply the same approach with the decreasing order also. Of course, you have to know the array is sorted in decreasing order in order to decide how to move the left index and right index. But once you know whether the array is sorted in increasing order or decreasing order, you can apply binary search accordingly. Okay. All right. So now we're looking at, say, a function whose values are either monotonically increasing or decreasing. So you may not know what is monotonic increasing, decreasing. So this is an example here. So let us pick up a function f of n is 2 over n square. So as my n value increases, as n is like, let us say n values are greater than 0. So if as n increases, starting from 1, f of n is like 2 over 1 square, which is 2. If n is 2, 2 over 2 square is 0.5. If n is 3, 2 over 3 square is 0.22 and so on. So if you plot n versus f of n, the values keep on reducing like this. Okay. So that's a monotonically increasing function. As n increases, the values keep on reducing. It's a monotonically decreasing function. If the n values keep on increasing as n increases, if f of n increases, that's a monotonically increasing. So just the name itself tells. So the monotonically means it will not, so if I say the function is monotonically decreasing, that means its value will either remain the same or decrease. It will not decrease and then increase and then decrease, again increase and so on. So it will not go like that. If I say monotonically decreasing, it will be either the same or just decrease like this. Okay, it will not decrease for a while and then increase and then decrease again and then increase and so on. It will not be like that. So that's what it's meant by a monotonic function. And whether it's decreasing or increasing, it's called accordingly monotonically increasing or monotonically decreasing. So this is a monotonically decreasing function, and what we want to find here is what is the smallest value of n for which the function value would be less than a threshold, or we can call a target value. So since we have to also call this n as a threshold, so let us make a difference. So we'll call the function value as a target. So and then we'll call this n as a threshold. So we want to find what is the minimum value of n. So that's why he used the word threshold. So what is that threshold or minimum value of n for which f of n would be less than a target value, say t is 0.01. So basically, given this function 2 over n square, where n is greater than 0, n is a positive integer, we want to find what is the smallest value of n for which the function value would become less than 0.01. Okay. Now, if you do a brute force approach of writing the different values of n, starting from 1, 2, 3 like this, and finding the function value f of n, you could do that. And as it starts from 2 and keeps reducing, keeps decreasing. So you have to find for what value of n the function value becomes less than 0.01. And you can see for n is starting from 15, the function value becomes less than 0.01. For 14, it was 0.0102, so it is greater than 0.01. But starting from n equals 15, it becomes less than 0.01. So this 15 is the minimum value of n for which the function value is less than 0.01. So you can find the solution using a brute force approach. But what is the problem? You have to try finding the function values for all these values of n starting from 1 to 15. So that will be like 15 times you have to solve this function f of n, okay, with the brute force approach. So now what we are trying to do is, using a binary search approach, can we find that threshold value by doing just log n number of times, by computing this function value f of n only log n times, not like 15 times, by doing something that is even less than 15, okay, and that's what we are going to do. We want to do less than 15 instead of just sequentially trying for all values of n starting from 1 to, you see, think about it, it depends on a function. So if you do a brute force approach, you may have to solve, say, that minimum threshold could be, say, 1 million or very large number. You cannot do that with a brute force approach, right? So binary search would be very useful for this problem. Alright, so what we need to do is, again, define an invariant. Where will be this threshold value? Okay, so we would say, again, we will define, let us say the threshold will be somewhere between the left index and right index. It could be either the left index or it could be the right index or somewhere in between. So we'll define our search space like that, okay, and similar to the previous application, we'll find the middle index as the average of the left index and right index, okay. So the middle index is somewhere here. So this now we will find the function value at the middle index. Now before that, one thing you also have to make sure, how you fix the left index and right index. That's very important. The left index is fixed in such a way that the function value, I did not show it here, but that's kind of, I mentioned that in the slide. So the function value, like, okay, so the curve is not very close to it, but okay. So you always choose the left index in such a way for this problem that the function value corresponding to the left index, which is this is the function value at the left index, right? So the function value at the left index is what? Is greater than or equal to the threshold, okay, so it's greater than threshold in this case, but in general we'll define this as the invariant. Where did I put it here? So I should have put it somewhere here. Okay, so the left index is an n value for which f of n is always greater than or equal to threshold value. So that is how you fix the left index. And you fix the right index in such a way that the function value would be less than the threshold. So at n being this value, the function value would correspond to something here. So this is our f of the right index. So at the right index, the function value is less than the target. So the target is this. Okay, so as I said, we want to find for what value of n the function value goes less than the target. So in order to find such threshold, we have to choose a broad range, a search space, comfortable enough that at the left index the function value is greater than or equal to the threshold, and at the right index the function value is less than the threshold. Now as you reduce the search space in the x-axis, the y-axis also, the function values will kind of fall in between these two ranges and will eventually reach very close to the threshold. Okay, so that's what we are going to see. So that's why you may wonder, what should I choose as my left index and right index? So given a function like this, and I say n greater than 0, you can try, you have to try some trial and error approaches for that. Let's try the first value of n, which is 1, and f of n comes out to be 2, and that's very obvious, it's greater than 0.01, our target value. So, and we know that's a monotonically decreasing function, so the function values can only reduce from here. We cannot go above 2 as you increase n. So we can conveniently assume this n equals 1 as my left index. Some may ask, why can't I assume 2 as my left index, because 0.5 is also greater than 0.01. Yes, you can start with left index as 2 and go further. The final result will not be dependent on that. Okay, so as long as you pick some left index at which the function value is greater than or equal to the target, you are fine. So we'll just pick 1 as my left index. Now what to choose as the right index? Now the right index has to be something where the function value is less than the target, and you see it is 2 over n square. Okay, so you could choose for some large value of n such that 2 over n square would be less than 0.01. So I chose 100 as my right index, because 2 over 100 square is such a small number that is less than 0.01. Now why can't we choose something other than 100? Yes, you could choose even 50 as your right index, because 2 over 50 square will also probably be less than 0.01, so you could choose 50, or even 1 million, or even 1000, 10,000, anything that could be chosen as right index, as long as this invariant is property satisfied, it is less than 0.0 the target, you're good. So once you choose your left index and right index, that's the range within which the threshold n will lie. We can keep going doing the binary search. Okay, so let us do a few iterations. If we cannot complete, we'll continue next time. So the middle index is always left index plus right index over 2 also for this problem. So which is 50 plus 1 plus 100 over 2 is 50, right? So again, we're dividing into two sub problems of equal size. So in binary search, we can assume in general the middle index is always the average of left and right index. Okay, so I don't see anything other than that for the middle index. Alright, so now what's the function value at 50? So 2 over 50 square is 0.0008, which is less than 0.01, that's our target. So that is something like this. At the middle index, we got a function whose value is 0.008, that is less than the target. So it means the threshold cannot be to the right of this middle index. As you see in this figure, it's a monotonically decreasing function. So threshold can be only to the left of this middle index, right? Or it could be at the middle index also, because we want to find the threshold value where the function value is less than the target. So it could be the middle index or to the left of the middle index. So that is why you move the right index to be the middle index. Okay, so you see here the way I define the problem. I say the right index is a value for which f of n is always less than the threshold, okay, or less than the target. So, and we want to find the n for which f of n will be less than the target. So, since I'm using threshold and target mixed up, so let me make things clear. So the right index is an n value for which f of n is always less than the target. The final answer could be the right index itself, okay, because it satisfies what we want. We want to find an n value for which f of n is less than the target. Okay, so for problems like this, you carefully define the left index and right index in such a way that at the end, one of the two will be your ultimate solution. And in this case, we define the right index in such a way that at the end, that the value of the right index will itself become the solution, because it satisfies the definition that it is a value of n for which f of n is less than the target. Whereas left index cannot be a solution for this problem by the way we define it, because the left index is an n value for which f of n is always going to be greater than or equal to the target, and that doesn't fit within the requirement here. We want to find a value of n for which f of n will be less than the target. Okay, and the right index is defined here like that. So since the function value at the middle index 50 is less than the target, it cannot be to the right of the middle index. The threshold has to be only either at the middle index or to the left of the middle index. So we move the right index or set the right index to be the middle index itself. So you see we are reducing the search space by half. Instead of 1 to 100, we are searching now from 1 to 50. And now the new middle index is 1 plus 50 over 2, which is 51 over 2, which is 25. Find the function value at 25, it is 2 over 25 square, which is 0.0032. That's again less than the target. So that means we move the right index further to the left and set that to be the middle index, which is 25. And you keep going. Now you see, let's do just one more iteration. So now the new middle index is 1 plus 25 over 2, which is 13. And 2 over 13 square is 0.0118, that is greater than the target. So that means we have come across something like this. At middle index equal to 13, the function value is greater than the target. So the function value becomes greater than the target. If you go even further to the left, it will be in this range. It will be even greater than the target. So there's no point in going even further to the left. That's the time we have to move the left index. Now how you move the left index, that is something we have to decide. The left index has to be moved to the right, so we set the left index to be the middle index, because you see here the function value is always going to be greater than or equal to the target. So we can make it to be equal to the middle index. Okay, so left index is set to be this middle index 13. And we go further down. Okay, so we have reduced from 1 to 25 now to 13 to 25. So you see the search spaces keep on reducing, and ultimately you'll be finding it. So I encourage you to go through these iterations before you come next time, so that when we go through this in class, it will be more very clear. We'll stop with this and finish up this next time. Okay, so any question? Excuse me. So